Okay, I'd like to first thank everybody for taking the time to attend the webinar, and I'd like to thank O'Reilly for hosting this webinar on GPU supercomputing for finance. I guess first, by way of introduction, I'll give a little bit of background about myself, my credentials, so to speak. I've been what's known as a quant, or in the UK they would call it a rocket scientist in finance for 20 or more years. In that time, I've done a lot of work in different areas, different markets, worked and lived in many different countries. I've been, I guess, very lucky. In the last few years, almost 3 years, I've been playing with this new GPU technology as a way of supercomputing in finance and doing things faster and quicker and working with larger data sets. It's a pretty exciting technology, I think, and I'm hoping that I'll convince you that it's at least worth a look if you're in finance, and even if you're not in finance, it's probably worth a good look. So that's a little bit about myself, a short bio if you want to scan over that. And by the way, the advice on becoming a master plumber, I think, is still valid. It's something I've recommended to my son, and I will recommend to all. Now, in terms of what we're going to cover in this webinar, here's a brief abstract. I want to emphasize this is a fairly high-level talk. We're not going to be stepping through code or reviewing GPU kernels, the things that actually do the work. It's going to be a high-level view of the technology, its capabilities, and actually how it achieves some of its outstanding speed. Then I'm going to also put it in the context of finance, and I'll also kind of touch a little bit on some of the like any new technology, it has some wrinkles and so on, and advantages and disadvantages, and I'll highlight some of those along the way as well. So by the time you finish this webinar, you should walk away with a sense of how GPU technology works at a fairly high level, how it's been applied in finance at the present time, how it might be applied in finance in the future, and some of the darker sides of the technology, some of the consequences for the financial landscape. Okay. It's also the case I've divided the talk into 3 parts, which for me was a fairly logical way of presenting the information, and I think it makes it a little bit more digestible because it's in bite-sized pieces. The first part of the talk deals with the GPU technology itself. And we'll start with the definition. It always helps to know what we're talking about and be on the same page. Then I'm going to discuss the relative performance of GPUs versus CPUs, and we'll begin to understand why GPUs are so significant in terms of application speed up. I'm also going to discuss in that section as to why GPU technologies all of a sudden become important. GPUs have been around for quite some time, but it's only in the last year or two that they've really come to the fore, and people have started using them seriously. And I'll also say why I think that GPUs are a ×10 type technology. In fact, I think it's a many ×10 technology in different areas. And because of that, I think that they kind of do change the rules of the game. We'll also pause at the end of the first part to have a brief questions and answers so that we don't leave anyone behind. I don't want to get to the end of the talk and find that there was a question that someone was stumbling over some concept in part 1 and we're on part 3. So we will briefly pause between each of the parts so we can have some questions and answers and make sure everyone keeps up. In the second part of the talk, I'm going to discuss GPUs in finance, and they're obviously important characteristics from a financial point of view. Speed being one of them, handling of large data being another, and the real-time aspects of financial trading and risk. And then we'll have a brief question and answer on part 2 as well. The third and final part of the talk is where I will talk about some of the challenges that are being posed by this new technology, both from a technological point of view and from a policy, regulatory market point of view. I'll also touch upon how CPUs might change the financial landscape going forward, and then we'll have a final questions and answers. Where any questions we haven't already addressed, we can sum up at the end. And once we have a final question and answer, the plan is to skip through some slides that give additional resources and reference material. These are all in the slide deck, which is available as a PDF. But I'll just, as we do question and answers, I'll go back and forth between those resources in case anyone wants to take note. Okay, so part one, GPU technology. Let's start with a definition, because I guess it's always helpful that we kind of all agree on what we're talking about, all on the same page. So I'm going to define a GPU computer as a compute device that derives most of its floating point, that's the number crunching aspects of its power, from GPUs rather than CPUs. Now, it's always the case that GPUs work in concert with CPUs. For example, they don't have an operating system of their own, they don't do I/O and stuff like that, so the CPUs are required for that, but they do work alongside CPUs to solve problems. But I'm going to say it's a GPU supercomputer if, because of adding some GPU cards, the performance speedups we see on a given machine are in excess of 10 times. In other words, you have a fast CPU-based machine, you add some GPU cards, that turns it into a GPU computer. And I'm going to call it a GPU supercomputer if the performance gain we see for kind of numerical type applications, specifically in finance, is times 10 or better. And as you'll see in this talk, as the webinar progresses, oftentimes we see times 100 and in exceptional cases times 1000. So very significant speed ups. So hopefully we're all on the same page. And it's probably also, even though it's early in the talk, to actually have a sense of what one of these GPU supercomputers might look like. And you might be surprised to realize that if you're sitting in front of a desktop or even a laptop computer these days, you're very likely sitting in front of a GPU supercomputer. Any machine, less than a year, perhaps 18 months old, probably has a pretty high-end graphics card. And that, running alongside your CPU, can turn it into a supercomputer by my definition. You can speed up applications by 10-fold, 100-fold, and so on. In this particular slide, I'm showing a GPU compute card that has no video output. It's a headless card. It's just for compute. And you can put one of those in your desktop PC, and you can see very significant speed ups for certain types of problems, particularly numerically intensive problems. So if you have a concept of what a GPU supercomputer looks like, it's a desktop, but it's with one or more of these graphics cards built in. You can also put these graphics cards in server racks and stuff like that, so you can actually have a compute cluster. But the most common form you see is essentially a desktop PC with a GPU card, a very powerful GPU card that makes it into a GPU supercomputer. So let's compare the speed of GPU versus CPU speeds. This is specifically for floating point operations, compute-intensive number crunching. As you can see from the lower blue line, CPUs have made steady progress. They are getting faster. Clock rates are going up. But it's a gradual, steady improvement in terms of peak gigaflop output. And a gigaflop is a giga floating point operations per second. But you see from the green line, which is the GPU path, that not only is it more powerful, and it's actually becoming more powerful more quickly. The gap between the two is widening to the GPU's advantage. And there are good reasons to assume that'll continue for quite some time yet. So CPUs are getting faster, but GPUs are getting faster much more quickly, and the gap is widening. Now, another factor in terms of application performance is moving data around, in other words, accessing memory. And we see a similar story here in terms of memory access speed, getting data to and from the processing unit to do useful computational work. We see a steady progression for the CPUs. That's the lower line. But again, if you look at the GPU curve, it's quite dramatically improving, and the gap between the two is not only wide, but it's widening. So moving data, once it's on the card, and the memory actually lives alongside the processing units on the card, it can move data to and from the processing unit very, very quickly, much more quickly than the CPU. Also, I would point out that once the data is on the GPU card, the GPU is operating on it, it's no longer a burden to the CPU. There might be a bottleneck getting the data on off the GPU card, but once it's on board, it's exchanging data with the processing unit very quickly, doing its work, and that's effectively been offloaded from the CPU, which can get on with its job of running the operating system and other applications. Now, how does the GPU achieve its performance, and specifically this performance gap between CPUs? Now, CPUs, as we noted, are getting faster. They have many cores. I've heard of processors with up to 6, was it hex core by the end of 2010. But they do run rather heavyweight threads. That's kind of threads of execution. And the way they work is you can have typically 1 per core, 2 with hyperthreading. And so the number of threads that you can have is rather limited by the number of cores into the low digits. So for a 6-core, you would expect 6 to 12 concurrent threads of execution. GPUs are architected slightly differently. They have many more cores, and they run what's known as very lightweight threads. And so even a fairly modest GPU card, a GTX 8800, for example, from NVIDIA, will run tens of thousands of threads, or in excess of 10,000 threads. So a huge disparity in the number of concurrent computations that can be done side by side. So again, we see the issue here is that sort of CPUs are getting faster. They are powerful processing units, but GPUs are getting faster much more quickly. And the reason for that is a simple architectural issue. CPUs are more general compute units. They have a lot more logic. They're more difficult to lay out down in silicon, whereas the cores for GPUs are much simpler, much more focused on one task only, number crunching. Rather simpler beast in terms of the operations it'll do, but it does them very fast, and you can lay them down on the silicon in much larger numbers. So whereas we have CPUs by the end of 2010 being in 4 or 6 or 8 cores, we're roughly around about 512 cores for the current generation of GPUs, and that's likely going to increase or double every 6 months, 9 months, 12 months sort of thing. So GPUs are much more powerful, primarily because they can have so many more cores and run so many more concurrent threads, concurrent numerical operations. I also believe that GPU technology is a ×10 technology. I have a kind of rule, I call it the rule of 10. For a new technology to replace an existing technology, it typically has to be 10 times better or 10 times cheaper, and ideally it has to be 10 times better and 10 times cheaper. In this case, people already use CPUs for number crunching. So it's an entrenched number crunching technology. Why would we replace it with GPU or go to the even effort of reprogramming applications to take advantage of the GPU? It's because I think it's a ×10 technology in many respects. Now, first of all, in terms of speed up, if it's a numerically intensive and data parallel type of problem you're solving, we typically don't just see ×10 speed ups. We actually see times 100 is more typical, and in exceptional cases times 1,000. And then on a per gigaflop computational basis, GPU technology is 10 times cheaper than CPU, requires 1/10 the space, 1/10 less power, and power is related to cooling, so it's actually 1/10 less cooling. So it's a ×10 technology in many respects. In that sense, meets my kind of rule of 10. I think it'll fare well in terms of complementing CPUs at the very least, if not replacing them because they do slightly different things. I'd also point out that specifically for finance, the ×10 less space, the ×10 less power, and the ×10 less cooling are very critical pieces of the technology. If you have a data center in the City of London or in Manhattan, it's on prime real estate. It's usually in a building which has limited electrical power. You can't have all the power you want in the world, and you certainly can not have all the cooling. So if you can, in a compute cluster, let's say, have a compute cluster 1/10 the size, that's obviously a huge advantage in finance, where essentially data center room real estate is at a real premium, not just because it's on premium real estate, but because of power and cooling and space constraints. So it's a very useful technology for finance specifically in that sense, because it fits into a smaller power and space footprint. Again, sort of GPUs have been around for a while, so why now? Why are they important all of a sudden? Why are they going to change the landscape of finance? Well, they have been around for a while, and they have been quite powerful for some time. All they do is essentially number crunch. But until a few years ago, they were very difficult to program. They were actually primarily the APIs, the drivers, they were all focused on just graphical applications. And what changed a couple of years ago is the the GPU manufacturers, NVIDIA and ATI, started writing drivers and APIs or frameworks at a much higher level that allowed you to use these units for general computation. So the frameworks changed, the API changed. They actually started providing good development tools. For example, NVIDIA has a thing called the Nexus IDE, which plugs into Visual Studio. So whereas 2 years ago you had to be essentially a bit twiddler to take advantage of these days you actually have a choice of fairly high-level APIs, mostly based on C and C++, but that's changing slightly too. At the moment, you have a choice of 4 APIs, CUDA, which is from NVIDIA, OpenCL, which is from Kronos. That's kind of open, a much more open group of industry participants. For example, Apple, I believe, is one of them. And so it's a more open kind of API framework that includes CPUs and GPUs, and it's sponsored by many manufacturers. Direct Compute, which is part of DirectX, is Microsoft's offering, and that obviously only works with Windows. Incidentally, the other toolkits, OpenCL, CUDA, and ATI Stream, the offering from AMD, who owns ATI now, the other major GPU manufacturer. The other ones are multi-platform. You can do it for Windows, Macintosh, and Linux, and so on. But Direct Compute is Windows only. So what's changed is that you no longer have to be a guru to program and take advantage of these GPUs. In fact, if you're just a reasonably competent programmer or just sufficiently determined, you can start writing GPU programs fairly easily. So, quick technical summary of GPUs as a technology. So GPUs are graphics processing units. They're essentially very good for crunching numbers. That's what they do. That's what graphics is all mostly about. There are 2 manufacturers, NVIDIA and ATI, and each has its own offering of a high-level API and framework. GPUs are massively parallel, running tens of thousands of threads, and have fantastic floating point performance, in excess of a teraflop per card often these days. And just for comparison, a very fast CPU these days tops out at about 100 gigaflops. So there's a factor of 10 difference in just raw number crunching performance. Another thing that's changed is that these graphics cards now have more and more memory. The latest generation, I think, has about 6 gigabytes, and that's improving with each new generation. And that memory is very fast. Typically, the data exchange can be faster than the CPU with regular memory. So it means that you can actually put up onto these GPU supercompute cards quite large amounts of data and process them very quickly. And that data can also be streaming data. It can actually pass through the card. And there's a huge advantage to co-locating the data with the processing power, and I'll touch upon that a little bit later in the webinar. Now, speed-ups of times 10 are usually quite common. In fact, with very little effort. Times 100 speed-ups for data parallel problems are very typical with not much effort. And in exceptional circumstances, if the problem is embarrassingly parallel and so on, I've seen speed-ups of up to 1,000. It's also the case that you can actually fit many GPUs into one PC, so you can actually have a somewhat scalable GPU supercomputer simply by adding additional cards. And these cards are comparatively inexpensive. A high-end graphics gaming GPU, which again has all the logic and all the memory and and works with the APIs fine, is about $500, $600, and that'll get you a teraflop. NVIDIA also produces compute-only cards, for the industrial and business market. They're $1,000 to $2,000, and again, but again, in the scheme of things, this is tremendous power on a per dollar basis. Now, at this point, I guess that's a quick technical overview of GPU as a technology, and I guess Catherine will pause at this point and take some questions.
Yes, and we do have a few questions, Shep. First, at the beginning, Henry was asking, what's a heavyweight thread and what is a lightweight thread? And we did get an answer from one of the participants. Oh, go ahead.
It's this way. I can answer that pretty simply. Basically, CPUs and GPUs do computational tasks. And these tasks don't last forever. They come to a finite end, and then when one ends, you have to swap another one in and actually start work on that. Now that's called a context switch. Now typically what a heavyweight thread means is the cost of moving from one task to another, one thread to another, is quite high. High might be microseconds, but in a world which moves, which is at very high speed, those can mount up. So a heavyweight thread means that switching from one computational task to another takes a little bit more overhead. A very lightweight thread means you switching between tasks, computational tasks, is very quick, very lightweight in the sense that there's not much baggage. It means that you can actually move from computational tasks to computational tasks much more quickly in a lightweight thread environment than a heavyweight thread environment. And obviously, the more computational things that you can do in sort of in parallel and sequence, the faster your computations. Does that help? Catherine, you there?
I'm sorry, I had
Hello?
my headset muted. I said, yeah,
Oh,
can you hear me?
Yes, I'm
I'm
hoping
sorry, I was
that's
muted
like
and talking.
Okay, so that's a kind of high-level explanation as to why, in terms of just throughput, doing more calculations more quickly, lightweight threads are a better way to go, and GPUs are about lightweight threads.
All right, and so Jose was asking, how do you measure the cost of a heavy thread versus a light thread?
It's usually in terms of context switching. In other words, if you want to switch, I'll make up some numbers, but I'll make them kind of roughly rounded numbers to make relative comparisons. If a heavyweight thread takes 100 microseconds to switch from one thread to the next, in other words, one thread ends, the next one starts. So there's 100 microseconds, let's say, before the next unit of work can be done. Now, if that's a heavyweight thread, and a lightweight thread can make the switch in 10 microseconds, in other words, 10 times faster, you can see that the cost of switching from thread to thread is much lower. You should be able to push more threads through the computational pipeline, and you should get better performance. The ideal, of course, was imagine if a world in which the latency or the context switch was 0. Then that would actually be, so let's call it, non-existent, or infinitely lightweight threads. So the lighter the thread, the more throughput you can get in terms of computation.
Okay, excellent. And we just had one other question, and it was from Edgar.
Yes.
He was asking, when you were talking about GPUs and software, he wanted to know if direct compute works on NVIDIA and ATI GPUs.
Yes, it does. It's part of, I think it came in with DirectX 10, and we're on DirectX 11 or 12 now. So direct compute has been part of DirectX, I'm fairly certain, since DirectX 10. So if you have a card which supports anything north of DirectX version 10, it should support some form of direct compute, I believe.
Okay, and one other question just came in. I don't know if you know the answer to this, but Dan was asking if there were any IDE tools to work with the .NET framework.
The answer is yes and no. It's yes. There are some .NET wrappers. They're like some C# wrappers that allow you to access the API or framework. As to specific support within, say, Visual Studio, NVIDIA does have an integrated debugging environment called Nexus, but that's not really .NET. That's just can be used for any development within Visual Studio. But as to a specific .NET tool, there's a .NET wrapper, so you can actually call it from .NET, but there's no native, shall we say, .NET interface to the libraries. They're much at a slightly lower level. There are wrapper libraries, but there's not a .NET native library for these APIs.
All right. Well, thank you. You certainly know your subject matter. And that's it for now, so I think we can go on to part 2.
Okay, so let's move on to part 2. In part 2, we're going to talk about GPUs specifically in finance, kind of what they're up to in that space now, and I'll hopefully just give you a flavor. I'll show you a few demonstrations. Some stuff I can't show you because unfortunately the nature of this work in finance is it's a lot of non-disclosure agreements and so on. But I think I can show you some interesting trends. And what you should take away from this little part 2 segment is, I think, a sense of how GPUs are being used, their capabilities, and actually how, if you're in finance, you might start thinking of using these things as well. So applications in finance. Currently, I see GPUs being used for option pricing, derivatives, financial derivatives, quite a lot for risk analysis, algorithmic trading, high-frequency trading. That's where essentially you take real-time data, do complex event processing, try and pick out profitable patterns, and the machine itself might actually place the trades. Data mining in terms of tick data. Again, data mining in terms of finding profitable strategies from different types of data sets and so on. Basically, GPUs are very good for anything that needs large amounts of computation and or oftentimes large amounts of data. Now, I'm going to use I'm going to extend a joke from the real estate world. In real estate, apparently the joke is that there are only 3 important things you should know about real estate, and that's location, location, location. I'm going to extend that joke to GPUs in a number of ways, and I hope you'll bear with me. But the first one, what I'm going to do is essentially, the important thing you need to know about GPUs is speed, speed, and speed. In finance, if ever there was a business where time is money, it's finance. Typically, if you can do it faster or get to the punch before the next guy, you can make money. So there's a huge financial incentive to be faster than anyone else. It's also, in terms of technology, so traders are a pretty short attention span people, and speed impresses them enormously. So if there's any of you out there who are trying to pitch GPU solutions to their constituency inside a bank or something, go demonstrate to the traders. If you can show huge speed ups, you'll have an awful lot of support. Nothing impresses like speed. And the reason why speed is important, you can imagine a scenario in which, for example, someone is trying to buy a complex structure, and they phone broker 1. And broker 1 says, yes, a complex structure, I'll get back to you with a price in 15 minutes. Broker 2 may be using GPU technology as a supercomputer. Basically says, okay, I have a price for you. In other words, he's actually priced it whilst they were speaking. Now, even if that price isn't quite as good as the broker number 1, in this business, given time is money and people simply want to move on, book the trade, and do the next thing, it's very likely that that broker would actually get that deal. So there's a huge advantage to being faster than other people in finance. Another example is currently, risk and compliance typically lag behind, trading activities, sometimes by a day or two. And that's like driving with looking in your rear view mirror. Now, imagine a batch job, that typically runs overnight. If you can speed that up by 1,000-fold, it now runs in 45 seconds. You've actually essentially taken it to near real time. The other thing about GPU technology and supercomputing in general is if you can solve problems very quickly and look at data sets much more quickly, it means that you as a developer can iterate more quickly. Imagine a scenario where you're doing some development and it takes a week for some program to run before you actually get feedback as to what it's done. That means you can only kind of iterate the solution once every week. If you speed that by 1,000-fold, you can now iterate and actually play with the data, explore it more quickly several times a day. That's a huge speed up in development. I call it low latency development. Essentially, there's very few obstacles to you moving forward very quickly. And to give everyone a sense of what speed ups actually mean physically, if you want to have a sense of what they are, imagine a 24-hour day collapsed down by a factor of 10. That means the day is only 2.4 hours in length. At 100, the day is also all of a sudden collapsed to 15 minutes. At 1,000-fold speed up, all of a sudden a day is compressed into 90 seconds. And again, taking that risk example, an overnight risk job that took 12 hours, now it takes 45 seconds. All of a sudden, you're no longer driving, looking in your rearview mirror. You actually have real-time risk. These are huge added value items in financial services. So speed, speed, and speed. So in this little demonstration here, what I've done is I've connected Excel up to a GPU to price 1,000 options using the Monte Carlo technique. Monte Carlo technique is intrinsically very heavy number crunching, and using the features of Excel, it's taken 64 seconds to do 1,000 options on that basis. Now, within Excel, I've connected it up with a small software utility I wrote. You can see that, and this, by the way, is running on a MacBook Pro with a low-end graphics processor. It's still capable of doing GPU stuff, but it only has 32 cores. Bear in mind that the new ones, the new graphics cards have 512, and if you saw just a moment ago there, I'll run that again. If you notice, it's 64 seconds if you just do it in Excel, and it was 8 seconds if you simply connect it up to a GPU doing the same calculations but on the GPU. That's a factor of 8 on a very low-end laptop machine, all within the comfort and the easy environment of Excel. So here we go, sort of click on the calculation on the GPU. It's thinking. The other thing too is that when you do calculations in Excel, if they're long-range calculations, it ties up Excel. You can't use it for other things. Again, if you push the calculation off onto the GPU, it releases Excel to do it so you can continue working. The results come back. So faster pricing and risk. Again, extending the real estate metaphor, the next most important thing to know about GPUs is data, data, and data. Storage is cheap. Bandwidth and moving data around is cheap. Data growth in the enterprise is just growing leaps and bounds. In financial markets, it's even worse, I think, in terms of the sheer amount of data that's floating around. Electronic and high-frequency trading is exploding. Some exchanges now, more than 60% of all trades are purely electronic, and the volume grows dramatically. This just pumps an awful lot of data into the financial system. Now the question is, how are we going to make sense of that data? And ideally, in the case of finance, how do you actually profit from the data? You in some ways have to basically digest it and turn it into actionable knowledge. And that means basically analyzing it, number crunching, doing complex event processing on it and stuff like that. And GPUs, obviously, if you kind of follow us so far, are actually quite good in this area. Another area in which I think that GPUs will make a dramatic difference is in terms of visualization of data. The human eyes combined with the human brain is a wonderful data processor, pattern recognition engine. But we can only kind of assimilate the data, visually in enough quantity to make sense of it. Large tables of data really just pass us by. So data is going to be an important area for GPUs. Again, you can often co-locate the data with the processing power and get some quite dramatic, analysis done in a very short period of time. So new ways to look at data. I think this is going to be very important. I think with GPU power, we're going to be looking at data in real time. This is tick data, Microsoft. It shows, upticks are green, downticks are red, sideways ticks are gray. It shows the open, high, low, close. It's just an interesting way to look at the data. It's dynamic. It's living and breathing alongside the data. Tick data is alive when it comes in, streams in. So I think we're going to see GPUs used in new and novel ways to look at market data in real time. I think we're also going to use GPUs to analyze and visualize data to see new and interesting patterns. And again, in finance, typically we're looking for profitable patterns. This is a little demonstration here where essentially there's a stock universe here. The size of the circle is represented the capitalization, and the motion and other colors and so on are indicative of several dimensions of data. But looking at data in new ways will allow us to establish new patterns, not just to make profits, but also to spot risks. So I think there's two sides of the coin. There's profit and there's risk, and these new visualization tools I think will be very useful, and GPUs will help in that respect. I think I've already touched upon the fact that these cards now have quite a large amount of memory on board, and the memory is very fast to exchange data with the processing units. When I say co-locating here, if anyone's from a high-frequency trading outfit, co-location typically means locating the computer as close as possible to the exchange to reduce the network latency. I'm not talking about that here. I'm basically simply saying that if you can get large amounts of data onto a GPU card and co-locate it alongside the processing power to do useful and interesting things with it, there's a huge advantage here. And also because it's offloaded from the CPU, it means that you can use your machine for other things without being dragged down. That's another great advantage, I think, of GPU computing, where you can load up the data and just let the raw computing power go to work on it. In the meantime, just get on with your work. However, it has to be said that the bottleneck at the moment, because these GPU cards live on the PCI bus, oftentimes getting the data onto and off the card is the bottleneck in the whole process. But I think that'll improve with time with better bus technologies, and so essentially there'll probably come a point where the GPUs are actually built into the motherboard and so on, with much higher bandwidth and bus speeds and so on for exchanging data. Again, coming back to our real estate metaphor, sort of another thing I think you should take away, which is important, is real time, and real time. I can't help but note that essentially everything in the world is going real time. If 10 years ago you wanted to get your bank statement, that typically meant a trip down to the local branch, or you had to wait for your monthly statement in the mail. These days, pretty much everybody expects to get that information in real time, typically to their phone even. Now, I think the whole world is going real time, but I think finance will get there first because there's such huge financial incentives. We're also moving to continuous time in the sense that people expect access to this data all the time, and also in terms of mobility, they expect to get it anytime, anywhere. Again, I think GPUs will be very good for this aspect of finance, because it'll essentially deliver lots of added value data in real time, pretty much anywhere, anytime anyone wants it. GPUs are being used quite well in high frequency trading. This little application here is called Streambase. It's a complex event processing environment. It takes tick data in at one end, does complex algorithmics, and places trades and hopefully makes profits on the back end. That application recently was GPU accelerated. I think GPUs are also going to be very good in terms of trend spotting. This video is a little choppy, by the way, because it runs perfectly outside PowerPoint, but within PowerPoint it's a little bit choppy. This is essentially streaming Twitter data, and you can imagine it as a stream of information in which you can dip a ladle and pull out useful information. I actually don't know of at least one money center bank actively doing this sort of thing, where essentially they're trying to trend spot and are using social streaming media. For example, I'll give you a couple of examples. You can track particular mentions of stocks as a sentiment indicator. And you can also imagine a situation in which a product recall was first seen on Twitter before the news services. Obviously, that would have had a detrimental effect on a stock. If you can get there first, you can make money out of that information. Again, currently, typically, risk and compliance are laggards in the sense that they lag behind, trading activities. I think that's becoming less and less acceptable, especially after the crisis and stuff like that, where people felt risk didn't keep up with the events and so on. So I think you're going to see, in fact, from my experience, GPUs are being, first and foremost, implemented in the risk area to speed up risk, to actually make it real time. Again, I used the metaphor or the analogy that currently, risk being delayed by a day or two after the trading event is like driving, looking in your rear view mirror. With GPU technology, you can oftentimes make that near real time. That's a huge advantage. So, Catherine, I guess we're at the end of section 2 here. The third part is actually quite a short section, so I think we're good for time. Do we have any questions on part 2? You there, Catherine?
I'm sorry, I keep forgetting to unmute my headset. Yes, we do have some questions. Don't laugh at me. No, you can laugh. So back at the beginning of part 2, Tarek was asking, is there a real demand from finance to speed up their application with GPU? And he wanted to know what's the current offer/demand balance?
Well, basically in finance, there are many areas of finance, and not just trading, where if you do things more quickly, for example, if you take the risk reporting function again, management likes to know what the risk of their institution is. If they're getting it the next day, so if they get a risk report, say mid-morning of the following day, for all they know, they could have been involved in a train wreck. They just haven't caught up with it yet. If we can move that to real time, where they can actually see risks, as and when they happen in their trading portfolios or whatever, you can imagine you can take much more corrective action. You can take hedging. You can exit your positions more in a more timely and structured way. So it isn't just a question about you going faster to make money. It's going faster to actually save money in the sense of making fewer mistakes and having a better sense of risk. So there's apart from regulatory reporting, let's say, where you have to kind of file a report every quarter, there's almost no aspect of finance that couldn't benefit from a speed up. Now, obviously, there are higher added value items than others. There are risk reports in which are more urgent than others. But generally, time is money. You do it faster, quicker, and you get there before the other guy. Usually, you live and he dies. It isn't just a question about the money; it's a question about survival too. So I see a lot of demand. So I see a lot of demand from trading. I see a lot of demand, equal if not more, from the risk side to speed up risk to make it to keep up with the trading. Specific areas, things like high-frequency trading, data prospecting, they're all useful areas. And again, don't underestimate the power of doing things more quickly in the sense of iterating too. If you're looking for patterns in data and you have an algorithm that takes a week to run, you only get to choose patterns once every week. If that speeds up 1,000-fold and you can do it 10 times a day, you can actually find useful, profitable trading strategies much more quickly. At a higher rate. So there are many ways in which doing things faster is better. Although in part 3 we'll see that faster isn't better always, I'd have to say.
All right, so Andrew was asking, are any of the prepayment OA models already available pre-canned?
If he's asking if there are literally libraries for financial derivatives he can just pluck out of the internet, not yet. There's a good library called QuantLib, but that's not GPU based. If you're looking for specifically GPU financial libraries, in fact that's how I make my living. I actually write derivative models and stuff like that for GPUs for clients, but they're pretty proprietary stuff. They're not making this stuff available. I think you will see basic libraries go out there, but in all honesty, if someone has a model that they can profit from, they're not going to share it with somebody else. So the answer is, I think, yes, those libraries will come for the more plain vanilla type of financial instruments, but I don't see that happening yet.
Okay, and here is a question from Eric. He wanted to know if there's any way he could get that Excel code that you used for the sample that you ran.
It's in the resources section.
Okay, excellent. And then I'm going to mangle this name. It's Mayank. Asked, we've heard Monte Carlo option pricing and other option pricing methods that are optimized on GPU. Can you mention other frequently used computations in finance that you think can gain from the GPU?
Lattice methods, general numericals, PDE solvers, anything that's computation intensive and can be made parallel. So lattice techniques are another area. As I say, PDE, partial differential equation solvers. Whenever you have a heavy-duty number crunching job, if it's in any way parallelizable, you're going to see usually some significant speed up if you move it to a GPU. So there's a whole swathe of quantitative financial models which will benefit from GPUs. Not all, but a large fraction, in fact the majority, are likely to see significant speedups if they're recoded for the GPU.
All right, and then Henry was asking about Rocket Boost. Is it going to support ATI card through Direct Compute or OpenCL?
Yes, all of the above. It supports ATI cards, NVIDIA, and Direct Compute, and so on.
Okay. And then we have one last question. It's from Greg, and he says it may be a bit off topic, but is the small investor able to trade at the speed of large institutions?
The answer is that they'll never be able to keep up with the big boys. One thing the big boys are already at the microsecond level. It's only a matter of time before they're at the nanosecond level. You soon realize at nanosecond levels, the speed of light is a problem. You have to co-locate your server within 30 or 100 meters of the exchange. That's going to cost an arm and a leg. So in terms of that sort of play in, an individual investor is never going to be able to do that. However, there's a whole spectrum of high-frequency trading. If you define high-frequency trading as, say, trading at time frames less than 5 minutes, in other words, you buy into a stock and you exit the stock within 5 or 10 minutes, then you can be located pretty much anywhere for that. It's only at the very, very, very short end that the big players literally co-locate their machines within very short, speed of light distances of the exchange. So there will be a whole swathe of individual investors with a GPU who can, on time frames of 15 minutes or less, do very complex trades. Where the network latency is a small fraction of the cost, most of it's computation, let's say. So the answer is those tools and those products aren't there yet. But I would say that before the end of 2010, you're going to see someone out there with a GPU card and a software application that basically moves individual investors into the high frequency sphere, not at the very low end, but anything 15 minutes or less, they'll be able to do some very complex event processing, tick data analysis, and so on. So the answer is yes, but I don't think that they'll ever be able to compete with the professionals.
Okay, and then Alexander, I think that Eric is asking how you get to the resources. I believe you have a slide for the resources at the end of your talk.
Yes, they're part of the slide deck.
All right. And then
Okay.
Alexander is asking a question. I'm not sure you have the time to address it, but he said, could you talk a little bit about storage retrieval of live tick data?
Oh boy, that's a big topic.
That's another talk in itself.
That's another talk, and I'm also a little bit mindful of the time. I have 7 minutes and plus on the clock here. So if you could take his question, I'm happy to answer that offline. But I would like to finish up the talk and have a little bit of time for question and answers at the end. Part 3 is a fairly short section, so I think we'll be fine. But as I say, I'm a little bit mindful of the time at this point, and that's a pretty open. Tick data is a fascinating area in itself. As I say, it's probably another talk, but I'm happy to answer the question. Would that be acceptable?
I think that's a good idea, so let's move on.
Okay, so part 3, here we come. So GPUs aren't without their challenges, and I'll also say a little bit about what I think the future is in terms of the landscape of finance when GPU technology becomes more ubiquitous. And the first question is, and this has already been raised by I think some of the questions being asked, is faster always better? And the answer is no. As we saw during the recent financial crisis, we had incredibly complex models of these things called CDOs, collateralized debt obligations, and CMOs, collateralized mortgage obligations. Incredibly sophisticated models, and they turned out all to be wrong. Now, if we calculate those at a 100-fold speed increase, then we're just wrong more quickly. So it's not a panacea for better financial markets. We still need to get the models right. We still need to get the market structure right. We still need to get the regulation and policy right. Doing things faster is better, but only if you're getting the right answer. And there are aspects of the business that don't require vast speed ups, reports to regulators on a quarterly basis. However, I would point out, going back to my earlier point about real time, everything is going real time. Eventually, regulation will be, reporting will be in real time too. And there are some problems with the GPUs are a poor match. There are algorithms which don't fit well into their computational model, and you're not going to see great speed ups. So leave them on the CPU. Now, another open issue, I think, is machines are making going faster, processing more data. As we see with high-frequency trading, the machines are making the decisions. In fact, humans couldn't couldn't even keep up. I remember talking to Catherine yesterday, and she was saying about open outcry orders and stuff like that. Some of these trades are now so fast that by the time the brain would to signal the jaw of an open outcry trader to move his jaw to place an order. In the modern high-frequency trading world at the very fast end, not only is the trade being placed, they've actually gone in, got out, and made a profit. So machines are making decisions at very high speed. Is that good or bad? I think that we've not been in this place before. So do they add to or detract from market stability? They inject liquidity, they increase volatility, decrease it. They're all open questions, and they're all important ones, and GPUs are going to make things even faster. But I think we better start finding some of the answers to these open questions of machines basically making more and more of the decisions, albeit under some sort of direct programming from humans. But again, once they're let loose, they're doing their own thing. I do feel however, that the genie's out of the bottle, and we can't kind of roll things back. We're going to have to adapt to this new world. Rather than roll it back. But I think there are some important questions. And when markets turn ugly, they can turn ugly very, very quickly. So with that little clip, that was sort of some commentary on the May 2010 collapse of the Dow. I think it went down 1,000 points in a very short time. So when things turn ugly in financial markets, they turn ugly very quickly. And as I say, sort of when everyone's rushing for the door, it's not always good that everyone's moving so fast. So there are some dark sides to this technology of things moving more quickly. I also feel as if the regulators aren't keeping up at this point. It's important that the exchanges, the regulators, and the market participants do be mindful of the speed at which they're moving, and that things can go wrong. I think there might be an arms race almost between the trading side of the business, who obviously want to move quickly and make money, and the regulators who obviously want fairness and market stability. And I think the only way the regulators are going to keep up in that arms race between the two is essentially by adopting the same technologies. They're going to be using GPU supercomputing and so on. But they're a good deal behind at the moment. So the future. Finance has come a long way with technology. Technology has been a driver in the business for many decades now. One thing I would say is with GPU supercomputing, providing some performance improvements of times 10, times 100, times 1,000, these speed ups are so significant, I feel, that they're going to change the rules of the game, both in good and bad. Good in the sense that, for example, moving risk to real time would be a huge advantage. Again, not looking like driving in your rear view mirror. So I think GPUs will do very well in finance. They'll do well generally, but finance specifically because the financial incentives are so high. But they will change the rules of the game to be moving at this speed at such a low cost. So I think that they'll change the landscape, and overall they'll brighten the landscape as a whole. But certain areas of the landscape will be thrown into shadow, and that's where we really need to look and think very hard and long. So it's an interesting technology, worth looking at, but not without its risks and wrinkles. And I guess we'll have some final questions and answers, Catherine? And I guess whilst we're doing that, I'll skip. Whilst we're doing that, I'll skip through some of the results.
Sorry, what were you saying?
So just people can have a sense. I'm saying whilst we're having some questions, I will skip through the resource slides at the end, just so people have a flavour of what's available on the slide stack.
All right, and I also want to open this. Let me see. Open this pod so they can download. There are a couple things you can download here. If that is showing up on your screen right now, let me check.
Mm-hmm. I'll just get through these and I'll answer questions at the same time. So
okay,
these are all on the PDF slide stack as well, right?
Yes, and this is we have his PowerPoint here and a poster, a GPU poster that Andrew sent. So go ahead, Andrew. Or do you want to talk about this, or shall I?
I guess if we have some final questions, I'll happily answer those. And I'll just flick through these resources here, I guess. Do we have so many final questions?
Yes, we do. Henry was asking, are some ETFs that seek to mirror an index or inverse of something just HPC, program buying, selling? I really don't know what that means. I'm sorry.
Okay, HPC is usually high performance computing. Basically, ETFs seek to be like a stock, but they're really an aggregate collection of stocks, like a little portfolio. Now, those can be constructed in different ways, and often they're constructed with fairly heavy mathematical models. So again, if an ETF is to work with an ETF in terms of its underlying data and so on, is computational data intensive. GPUs are a good candidate. I know that HPC, high performance computing, is used with ETFs already, electronically traded funds, I believe. They're stock like they behave like a stock, but they're really more than a stock. Already HPC is being applied. Think of GPU as just another form of HPC, but it's typically at a price point. An accessibility level well below where HPC. Oftentimes HPC, high performance computing, when I talk in finance, we were talking about $500,000, $1 million as a compute cluster. That same sort of power now, just a couple of years ago, is in the form of a $2,000 card. So if he means HPC is applied to ETFs or any other type of instrument that's either mathematically complex or data complex, then look at GPUs. There might be a very cost-effective solution.
All right, that's a good answer. You're being asked if you could go back to the resources slide.
Okay, let's go back. Boom, boom, boom.
All right. And while you're doing that, can you tell? Are you Rocket Boost on Twitter? Is that if people want to follow you?
Oh yes, so Rocket Boost is the little kind of is the software layer I wrote so that you could access GPU supercompute power from within the comfort zone of the reality is in finance, Excel is the front end of choice. Simple as that. Traders, risk people, middle office people, Excel is the front end of choice. There's no getting away. It's a great tool in some respects, but it's poor at number crunching. Rocket Boost is a simple piece of software I wrote that allows you to very easily call GPU supercompute functions from within cells in Excel, and it looks they look and behave like intrinsic Excel functions. Okay. It's still kind of in beta development. It's still not there yet, but as I say, if you like the familiarity of Excel and the power of Excel, but want to tap into GPU supercompute resources, it's something to look at. Okay, good. Now I have a couple more questions. Henry's asked a couple good ones. He says, is GPU's floating point precision good enough for financial computing? The latest cards support IEEE, was it 754, whatever it is, double precision floating point. So if you have a, for example, an NVIDIA card with a compute capability of 1.3 or more, compute capability is basically just a little numerical handle that tells you what its computational abilities are. I think from compute capability 1.3 and above, it's had double precision. So it now has the same precision as a regular CPU. So it used to be only single precision floating point, but now it has IEEE double precision floating point. It doesn't run quite as fast as float single precision. But again, you can do the experiment. You can write your models in single precision, and if they behave well, even in corner cases, then stick with single precision because it's faster. But you do have the option with the latest generation of GPU cards to do it in double precision, and that's the same precision as CPU.
Okay, and then a related question, I think it's Peng is asking, does it matter to finance applications that GPU is not 100% compatible, I think he means, with the IEEE floating point standard?
Again, if you're doing this sort of work, the best thing to do is to write an awful lot of unit tests that test the corner conditions. I always start with single precision floating point and do my test there, because if you can stay in that domain, you're going to be faster even still. Only if you have numerical stability problems. But this is true of numerical stuff that I do on the CPU too. I'm very careful to test corner conditions. There are slight wrinkles with double precision on GPUs, but I've not found them to be an obstacle to port in an awful lot of code that was double precision CPU and making it run on the GPU. But again, with any of this numerical stuff, precision is always an issue. You should always be writing your code and testing it and doing the corner cases and so on. I always start with single precision floating point and see how far that gets me. Only if that produces some problems do I actually move to double precision. But I've not had major obstacles or problems going from double precision on CPU to double precision on GPU. I'm just speaking for myself.
Okay. And then I thought Henry had another interesting question. He said, is loading large data into GPU's memory still a problem in terms of latency? And if so, how do you solve that? How do you load the live feed into GPU? Or is it only capable of calculating a snapshot?
No, you can stream data through GPUs. You can still stream data, but he is correct in the sense that the bottleneck, oftentimes with with using data with GPUs, is getting the data on and off the GPU cards, because they sit on what's known as the PCI bus. Now that's a pretty fast bus, but these days these things are moving so fast it's difficult to keep up. Now, one little tip I would give, was it Henry who asked this question?
Yes.
One little tip that I'll give him that has proven useful for me is that the GPU is a memory-rich and computational-rich device. Getting data across the PCI bus is often the times the bottleneck, but because you have so much raw computational power on the GPU, one thing you can do is actually compress the data, push it across the slow PCI bus, and then decompress it in real time on the GPU where you have all the power in the world. So if you can have a, say, 10-to-1 compression ratio, you can obviously imagine that it moves onto the card 10 times more quickly. So it's a trade-off. You have to do the experiment. So one way of getting around the PCI bus is to compress data and then decompress on the fly on the GPU, because essentially 1/10 of the data had to go across the bus, even though 100% of the data is available on the card. It's also the case, I think, that we're going to see more and more of these GPUs on motherboards where they've either designed a specific bus for GPUs, or the GPUs are actually being built onto the motherboard with a much higher bandwidth. Now, that's probably a year or two away, the latter part, where they're going to move onto a higher bus. In the short term, they're going to live on the PCI bus. But as I say, one thing that has worked for me, for example, tick data compresses quite well, is see if you can compress it. You can either compress it as a block, or you can stream compress it. And because the CPU, so the GPU has so much raw compute power, oftentimes the trade-off is much better to compress it, get it across more quickly, and then process it, decompressing on the fly.
Okay, that makes a lot of sense.
So, but that is a real obstacle in terms of large data sets, is getting them on and off the card. And you can set up things too where essentially the data streams through the GPU card.
We have some questions about hardware, and one gentleman is asking, would you recommend the new NVIDIA GTX 460 for GPU development? And then another person is asking, which hardware vendor has a more stable API implementation as of now? So
fairly easy. Just so people know, I'm not a spokesman for NVIDIA. I don't own NVIDIA stock or anything like that. But the simple reality is that in terms of APIs, we had CUDA, we have ATI Stream, we have Direct Compute, and we have OpenCL. From my experience of being around on the forums and so on, CUDA is by far the most popular API, and that's from NVIDIA. OpenCL is getting more popular and gaining ground. Direct Compute, I think, will do very well because it's from Microsoft. ATI is a perfectly good API, but it doesn't have the same traction as the others yet. So in terms of demand, in terms of what I see people wanting to implement, CUDA is the most important one at the present time. If that's the case, then any card from NVIDIA obviously has a slight advantage because you're on the most popular API. That's just my unscientific, sampling of working with people. People are doing most of their work on CUDA rather than the other APIs at the present time. That might change, but I'm saying that's where we are now. And any of the new NVIDIA cards, the 400 series and so on, I think they're all compute capability 2.0. They're very fast cards. They have 400 plus cores, often with a lot of memory. So the answer is yes, I would happily use an NVIDIA 400 series card, and I would do the work mostly in CUDA.
Okay, good. And then we have a couple specific questions about packages. Are there any finance packages that are using OpenCL as of now? And
that are publicly available rather than proprietary? The answer is no.
Okay.
I do know people inside hedge funds and money center banks who are doing OpenCL development, but it's all proprietary. These people are hoping to make profit from these libraries. They're not going to share them. Most of my work is under NDA, non-disclosure agreement.
Well,
so the answer is, I think that those libraries. I think that they're if they spend $1 million developing a library, I very much doubt if they're going to share it. Having said that, there's a thing called QuantLib, which is a very good open source contributed library. It's not GPU; it's purely CPU based. And that's changed. But I'm sure that there'll be enterprise in minds out there that'll make it GPU compatible or OpenCL or whatever. But that's going to take time, and it's always going to be the case, I think, that you'll never get the best libraries out there because people are making money out of it. If I'm making $1 million a day from high-frequency trading, I'm not going to share those algorithms with anybody.
That does make sense. So one more question. It's pretty general, and I actually think that you covered this, but I'll ask it. Where has GPU seemed more applicable, streaming real-time or heavy number crunching?
Heavy number crunching so far. It's only more recently I've seen more kind of streaming applications. So far it's really been like I have this huge portfolio, optimize it for me. I have this huge portfolio work out the VAR for me. Those are kind of like one-off, crunch the numbers. I'm seeing more activity like that bank that's dipping into the Twitter stream and so on. There is more interest in streaming data because there's so much of it in finance. Pretty much most data in finance starts life as real-time data. It's streaming. It's just the tools for that aren't as good, and it's a little bit more tricky to program. So generally speaking, most of the work I've seen and done is crunch the numbers, use this data, crunch the numbers, or just crunch the numbers. But I am seeing more interest in, I have this stream of data. I think it's highly valuable. I want to be able to analyze it in real time, make decisions, and have actionable items from it. More tricky to program, but that is coming along. But it's a more recent trend.
All right. Well, I think we're out of time, and you've answered all the questions, and this has been absolutely fascinating. So I want to thank you, Shep, and I want to thank everyone who joined us today, because we've had a very knowledgeable group, and it's been fascinating watching the chat room. So
it's a fantastic. I find it a fantastically interesting area. I think it'll do very well in finance.
Yes, and
if you're in finance, it should definitely be on your radar screen. And I think it'll do well generally as well. When you see speed ups of times 10 or times 100, this kind of changes the rules of the game. It most definitely worth keeping an eye on at the very least.
Yes, and so people are asking about the recording. We'll have it available in. It will probably be early next week. It takes us a while to. Oh, Andrew, what is your Twitter name? People want to follow you on Twitter.
Rocket Boost.
Rocket Boost, that's what I thought. So we'll have the recording available probably early next week, and I will send an email to everyone who registered for it. If you came in without registering, then you can find the embedded YouTube version on our webcast page, which is O'Reilly.com/webcast. You can also find it on our YouTube channel. Just go there and search. And we also we'll have the recording available as an archived Adobe Connect recording, which is nice because you can still download the files and the links are live and everything else. It's like being here in the live webcast, except you can't ask questions. But I'll send that out to you probably Monday or Tuesday. So thank you, Marcy, for putting those resources in. And once again, thank you, Andrew. Thank you, everyone else, for doing this. It was a great webcast. So I'm going to count down from 10 and then close out the room.
I hope people enjoyed it.